it's a little bit hard to tell, whenever you write a talk ahead of time for an audience, who the audience is. So there's a lot of stuff in there. So it's kind of whatever you guys are interested in, what do you guys want to dive into detail, please ask questions. And I will try not to lie. Basically, it's my only. I'll answer them to the best of my ability. Thank you. Beautiful.
So let's get started.
All right. So I'm going to talk about OCaml in general, specifically kind of about the deploy targets, about some of the characteristics of OCaml. Start out real quick. I'm a developer. I generally work in Clojure and OCaml most of the time. So those are two different. How many of you guys are familiar with Clojure, the Lisp on the JVM? How many of you are familiar with OCaml? Okay. For those of you, they're very different languages for those of you who are not familiar with them. But it's an interesting kind of position to be to compare and contrast the two. For the purpose of this talk, I'm basically a hype man. I'll try to be a semi-responsible hype man. You guys are, feel free to bring me up on anything. And as a caveat, this is a really short talk. There's lots of stuff left out. And it's basically, we can treat it as a thought experiment in lots of ways. So real quick, we're all kind of familiar with app dev goals. Basically, we really want kind of correctness, fewer bugs. We want to be able to deliver our product really quickly. The product should run very well. We want to ideally have lots of code reuse, right? We don't want to repeat ourselves if we don't have to. Security is oftentimes a concern that isn't given due consideration, but it is something that is important. And we want to write maintainable code. We're all kind of familiar with these ideas. Whenever the rubber hits the road in the real world, though, this is kind of an order list where it goes something like, we need to be able to deliver quickly, we need to be able to deliver quickly, and so on. And then kind of at the bottom, it's like, well, by the way, we also want to be correct, fast, secure, everything, right? And I actually think this is kind of fair, right? In a lot of ways, business goals are very important. It's not sustainable if we take a very long time to deliver a product, and we don't have a chance to kind of invalidate our business hypothesis. But on the other hand, kind of developer happiness and operation happiness is very important as well, right? If you are, we've all been in a code base, generally speaking, that we are not very happy about, and it is a struggle to kind of, you can hear the timer ticking down for how long you're going to be at that job until you get into a better code base. So I try to kind of figure out, what's the balance? How do we strike a balance? I think OCaml might fit an interesting space, or an interesting spot in the space. So real quick, who of you have used OCaml either at university? Anyone use? Oh, wow, 2 hands. Okay, I expected a little bit more. How many of you have used it at a job then? Okay. Oh, okay, 1. Okay, great. How many of you enjoyed it of the 3 people? So just for those of you who don't know then, it sounds like I can kind of go into the detail a little bit. So OCaml has an incredibly lightweight but thorough type system. It's a bit like Haskell in that sense, lots of inference. OCaml implementation has a strange obsession with performance, actually. It's worrisome at times. It's statically compiled with very, very predictable characteristics. There's no JIT. You can look at the assembler outputs of the compiler and have a very strong intuition about how the performance is actually going to be. It has a lot of different deploy targets, has highly efficient JavaScript output. The execution model of OCaml maps very, very nicely onto modern JavaScript engines. You can build UIs with it. It compiles down to ARM64. So you can use this, for example, to build mobile apps as well, or you can run it on your Raspberry Pi. And it tends to encourage a functional style, but it doesn't require it. And this is particularly nice kind of at the edges of the application, right? Oftentimes you want your core to be functional, but you need to interop with either a legacy system or with some kind of highly effect-oriented domain. And so it's really nice to kind of be able to fudge things at the edges there. But kind of strangely, because of the obsession with performance and correctness, but also the high-level expressiveness, it's actually really well suited for both systems programming and app development, which is not traditionally kind of thing. You have Rust and whatnot, which is very, very kind of systems-oriented. You have things like maybe Ruby, Python, Java, etc., which are much more kind of app level. So OCaml does kind of a good job of straddling those two different ends of the spectrum. So as an example of a deploy target, you can write OCaml programs and run them on Linux and Mac. Going into detail, there's not much to say here, right? We all do this. But kind of a more esoteric target, and one that OCaml has been doing a great job of leading via the Mirage OS, is Unikernels. How many of you guys familiar with Unikernels? All right. So Unikernels, real quick. So very like a kind of new way of building applications. There were a lot of these ideas in the 90s. They've only kind of recently become realistic in many ways because of virtualization, where we actually have a standardized hardware profile that we can target. But the idea in OCaml, at least with Mirage, is that rather than having this huge monolithic Linux kernel, which is 15 million lines or more of memory unsafe C, that whenever you want to write a simple program, you pull all of that in. We're going to say, well, we're going to write an entire operating system in OCaml, but as a library. And at compile time, you only pull in the libraries that you actually need. Right? So if you need a TCP stack, we'll pull that in. But if you don't, we don't put that in. Right? And that's actually very, very difficult to do with traditional kernels. So this means that there is a lot of pure OCaml implementations of very, very low-level system libraries. So things like TCP stacks, implementation of TLS, different forms of data storage. Your application will actually compile ahead of time, and you only pay for what you use. And what this means is we actually compile not to a typical like ELF binary or anything like that, but we actually take your application, we will compile it, we'll pull in the exact libraries that you need, and we'll create an entire VM that will boot up. So your application is now the VM. There is no Linux kernel. There's no like operating system. It is just your application, which is why it's called Mirage, right? The OS is a bit of Mirage, actually. It's just your application running on the VM. And so this has lots of like very interesting applications. So yep, your app is the VM, and you get some really, really cool small numbers here. So now we have thousands of lines of memory and type-safe code versus millions of lines of memory unsafe code. This has pretty severe security implications. The surface area alone is considerably smaller, excuse me. It's considerably smaller, right? So if you think about the Linux kernel, how many of you, well, I mean, no human being can hold that in their head, right? 15 million lines of code is a lot of code. Well, I don't want to generalize. I can't hold it in my head. But actually, with the OCaml implementations, you actually can. You can actually traverse the entire stack on your own. And part of that is due to the fact that it's a memory-safe language, so there's a whole kind of swath of implementation details you don't have to worry about. Part of it is the type-safe nature of it, but largely it's just due to the size because of the expressive nature of OCaml. So whenever we actually compile, please.
What's the coverage of, thanks. What's the current coverage of OCaml libraries when you compare it to kernel, for example? Is there anything missing that we may want to use?
Sure, a lot, right? So actually the way Mirage and the Unikernel stuff started is a group of pretty crazy people out at Cambridge about 7 years ago who were like, let's just rewrite everything from the ground up in OCaml. And 7 years is a while, and they've been able to do a lot, but not everything. So they kind of started with the core, so stuff like TCP stacks, DHCP servers, TLS implementations, this kind of stuff. But there's kind of always going to be the edge, or the envelope of stuff that you might be missing that you're used to in a Linux kernel. So whenever you actually do compile down your VMs, you end up with these very, very tiny artifacts. So if you kind of imagine if you were to optimize a Linux installation, you could probably get it down to hundreds of megabytes, maybe. Anyone deploy Linux servers with smaller than that? So a few. All right, cool. What's the range, maybe?
20, 40 megabytes. 40 megabytes.
5 megabytes. We got 5 megabytes. It's pretty good. And is it easy to do that?
Yeah, Alpine.
Oh, so Alpine is actually quite good at this, right? So some of the newer approaches have actually been quite good at kind of emphasizing being able to dissect this. And then I'm curious about boot times as well. Like whenever you boot a VM on Alpine with a 5 megabyte image, how long does it take before your application is up and running?
That's pretty instant.
So like instant meaning.
Like in milliseconds.
No, very nice. Yeah. So the goal is to make it so that everything by default is like that, right? So whenever we build an application, we want to be in the range of hundreds of kilobytes to maybe low tens of megabytes. And boot time is typically around 50 milliseconds right now for your entire application. So your entire VM and your entire application. And this changes a lot of what we can do with actually development and deployment, right? Where now, because these are so small, you can actually check in every single VM that has ever been deployed to production. So you can actually have a Git repository where we're going to have an entire audit log of anything we have ever deployed. And this has big kind of implications for, for reproducibility. So for example, if there is an error in production, you can actually go to that exact VM and reproduce the state pretty trivially.
So do you check in binary blobs or source?
So both. So you have your source code, which is, of course, we just traditionally have the version control system with it. But as part of the build system, right before we push to production, we actually push to this, we do a git push of the binary blob of the VM image into another Git repository. And so that's kind of our entire audit log of everything that's ever been deployed as an actual artifact. So repro cases are significantly easier, right? It is much nicer whenever, rather than getting an email, like an error trace, and you get to say, like, play computer in your head, try to figure out how the user hit this or how the error actually occurred. You actually can save the state and save the VM, pull it up, and have an instant repro case. There is some work actually in this area. So Mirage is traditionally oriented or targeting the Zen hypervisor. There's some work with the Solo 5 stuff to actually get it to run on KVM, and they're targeting kind of 20 milliseconds in boot up time, and maybe smaller than that. So this also means that it changes the way that actually deploying application, not only deploying, but booting applications works. So we have this idea of just-in-time summoning. So where a request comes in, because 50 milliseconds is actually shorter than, shorter than the reply window for a TCP connection. So literally we can have a TCP connection come in, and we can block on that. We can boot up an entire VM just to handle this one connection. We can then give back the IP, and then have them kind of finish the session, and then just kill that VM. So because these VMs are so small and they boot so fast, we can actually, for an incoming TCP connection, just boot up another one entirely, and then just kill it whenever we're done. The idea is kind of like a dust cloud, they call it, right?
How's it like to operate these Unikernels? Like in Linux, we have the standard tools like the various stops, netstart, and whatever. But when you use these Unikernels, you don't have that, right?
No. Yeah. So it's kind of this entirely different way of thinking about it, and it's caused me to reflect a little bit on what kind of Unix development actually is like right now. And Unix development, like with a shell and whatnot, is a bit like an ad hoc REPL, right? Where you kind of go in and you have very strange function calling conventions and whatnot, like it's not standard. But you do have a lot of these tools where you can kind of poke at these different things running. With the Unikernels, it's kind of all happens at compile time, right? You're deciding exactly what's going to, it's a bit like Nix, right? Where you're saying statically, this is exactly what I want to happen in the exact order that I want it to happen. So you don't have these other tools. You just use the tools that are provided for you in the language, and you build your application. And I think it is actually analogous to the servers being kind of applications, right? Where we don't tend to think of the Unix kernel as part of our application, but actually if you think about like an app server, right, it is actually all there, right? That is our application. So using these different tools is analogous to function invocations in this kind of strange execution environment.
Does it mean that you need to rely more on debugging like at the hypervisor level?
Well, it depends on the specific case. So because all of these libraries are written in OCaml, it means that a lot of the debugging becomes very easy, right? You can actually capture a lot of TCP traffic and actually replay that in other tools. You can, yeah, so depending on like, so netcat, right, or SART, excuse me, it depends on, like, you have a bit more flexibility, but there's a lot more work required on your part to figure out how is debugging actually going to happen, right? It's maybe more ad hoc right now, rather than like the standard tool that everyone uses.
Hi, I was going to ask if you could do real time with this, but now I realize you're only targeting running in a VM, right?
Well, so this can compile down to, like I said, kind of real, or so smaller devices, so
Right.
Raspberry Pi and that kind of thing. But you do have a garbage collection here. OCaml is not traditionally meant for a real-time target, right? I don't even think soft real-time. Yeah. Sure.
Okay, what about the file system?
Ooh, good question. File systems are kind of sort of crazy in a way, right? Like if you think about kind of the complexity that a file system presents. And so this is one of kind of the tools that needs to be rebuilt kind of from the ground up. And so whenever the Mirage team in particular was thinking about this, they tried to take a different approach. And so they said, well, what if we just started with something very, very simple in the beginning where we could just store a bit of blob or whatever, depending on what you want to store. And we just had Git semantics. So they basically have implemented a kind of a database-like thing in OCaml called Ermin. And the idea is you store your data in there. It speaks Git, so you can actually store in memory. You do a Git push to a server, or at boot up, you do a Git pull, and you kind of pull the file system that you need in, maybe a shallow clone or whatever, and you operate off of that. But there's no kind of implementation of any existing file system as it stands right now. So this does require kind of a radical rethinking in lots of ways of how you do your application. It turns out to not be such a big deal, right? But a lot of the stuff that we take for granted, like existing tools or file systems or whatnot, kind of go away. Cool. Oh.
So I'm interested in how do you deal with these situations where you do need a tool that is missing in Unikernels, for example, image processing or access to file system. How do you, architecturally, how you solve it with this approach?
So I'll go over a little bit of this and like the OCaml caveats at the end. So I mean, part of the challenge with OCaml is like it does not have the ecosystem that something like Java would have, where you have these wonderful image processing libraries and whatnot, right? And so you are left to re-implement a lot of it on your own, or to set up some sort of external service. So I actually think we're moving into an era where we have a little bit more wiggle room because of the API-oriented nature. Like there's a lot of services that will do this stuff for you. So in our case, we use ImageX, which is this external service, kind of image CDN processing thing, and it works fairly well for us. But there are cases, or there are some attempts to do some cross-compilation and whatnot to bring some of the existing infrastructure out there into it. But then you are bringing in these big memory unsafe, binary blobs into your application. But the goal is to hopefully at some point give you the ability to choose where on the spectrum you want to be there.
Maybe it defeats the purpose, but can you link C libraries?
Yeah, exactly. So the goal here is to be able to do that. But like I said, you bring in these blobs, but at least you have the choice, right? So you can kind of choose where on the spectrum you want to be, and hope, in an ideal world, everything would be implemented in OCaml and whatnot. But oftentimes that's not a realistic thing, again, for, if we want to ship sometime this decade kind of thing, right? So there is work on being able to bring in kind of arbitrary C libraries. Cool. So on the other hand, you get these really big numbers for unikernels, right? So whereas previously maybe we could run hundreds of VMs on a piece of hardware, now we can run thousands or tens of thousands of them, right? Because they take up so little, we can boot them so quickly and throw them away so quickly as well. Another deploy target is JavaScript. Any of you guys JavaScript front-end developers? I can kind of skip through if it's not super interesting. So we can take that same code. So we have pure OCaml implementations of TCP stack, TLS, all that kind of stuff, right? We can actually take that and compile that down to JavaScript. We can share type definitions, modules, etc. And pretty much any OCaml code, any pure OCaml code, just works. And so this has kind of interesting implications for example, debug tools. So for example, if you were able to record all the TCP traffic that was coming into your unikernel, and you maybe set it aside, for a given session. And if there was an error triggered, you just stored it. And then later on, what I want to do is actually build a little in-browser tool that would bring in that TCP stream as it was recorded and would actually render it in the browser. And I would know that I'm using the exact same code that was used on the Unikernel as is used in the browser. And this is not for like creating connections or anything. It's about maybe visualizing the TCP stream and understanding what was going on. But now I know that I can very, very reliably bring in this tool, replay the session, actually use a lot of debugging. The kind of debugging tools I can build are very, very different now.
How do you get this efficiency with ASM.js or something?
No, so actually it's just the natural model of, so OCaml relies on a garbage collector, and with ASM.js, there's no hosted interrupt for the GC or even WebAssembly right now. But just kind of the execution model is highly amenable to kind of V8 optimization and that kind of thing.
What's the interop like between OCaml compiled to JavaScript and JavaScript library?
Sure. Maybe I should reorder my slides. So there are one of the big outside picture. One of the big problems with OCaml is there's like 2 of everything as a minimum. So there are like 2 standard libraries. There are 2 async libraries. And there are now 2 JavaScript transpilers. The old one is very, very efficient and has lots of optimizations that are very interesting, but it has kind of a closed world assumption where interrupting with the outside world is kind of a tedious thing where you need to kind of manually type everything. Also, it doesn't understand JavaScript modules and kind of all the stuff that has been happening in JavaScript. There's a new one out of Bloomberg called BuckleScript, and that has been written from the ground up specifically to, like with this open world assumption of we want to interrupt, we want to bring in the existing legacy stuff, or not even legacy, but existing stuff that's in JavaScript. And that has been doing a lot more work to kind of automatically infer a lot of the stuff and make it, so it also generates highly readable JavaScript, whereas the old one is all about how can we make sure that what we generate is very efficient. So there are 2 different kind of approaches to this right now. So if you guys are familiar with like Flow or TypeScript, OCaml, the type system, just basically gives you this stuff out of the box, but much, much better. I mean, they're both really, really cool programs, but it's really difficult to recover a lot of the typing information and make sure that you have these sound programs. And with OCaml, you're not recovering it. It's just from the ground up. You have it. And then the output size is generally very reasonable. So having worked with ClojureScript quite a bit, this was a big concern I had.
Can you do multi-threading in OCaml, or is it single-threaded?
Yeah, so you have async libraries, which are so kind of like Go style, lightweight concurrency and whatnot. But OCaml itself is single core, so you can do multi-threading and whatnot, but ultimately it's all going to be single core. There is a new release. Well, it's been in the next release for like several releases, but it's a difficult thing to do. But they are actually implementing multi-core, but they're implementing it via algebraic effect handlers, which has very, very interesting properties. And hopefully I'll be able to get to that. Yes?
What is the coverage of web APIs?
So on the JavaScript side?
Yes.
Little to none. So again, it's this idea of a closed, so with the more mature one, it was a closed world assumption. I have OCaml code that I want to run. And I'm going to bridge that gap to output or render or whatever as that last line, or last mile problem. So there's quite a bit of work there where you can pull in like canvas rendering and lots of stuff like that. But it moves much more slowly than even I think like the web standards are moving at this point, which is quite fast, right? They're releasing and they change WebRTC and WebAudio and kind of all this stuff very, very quickly. And so that's part of the goal of the newer approach is to be able to very, very quickly cover this stuff, even automatically cover it.
Yeah, I'm wondering how stable is the kernel API? If you say you can reproduce older versions of your stuff, is that still going to be true? Like if you take 1-year-old code will you still be able to?
Well, I mean, you should be able to, right? Because you're specifically bringing in the dependencies and whatnot of that. So like whenever your code is tied to a specific set of dependencies and versions and whatnot, right?
Okay, so it has the whole, everything you need is in there, and
exactly. It should be kind of self-reproducible, right?
Okay.
So self-describing.
Okay,
yeah.
Great.
All right. So another target is mobile. So this is one near and dear to my heart. So we can take the same OCaml code, compile down to ARM64. You can very, very easily interrupt with C, Objective-C, etc. So, I mean, building Android and iOS apps, fairly straightforward. Another one is Raspberry Pi. So again, I'm going to just do ARM64. And this is one area where the strange obsession with performance in OCaml kind of pays off, right? Because these are smaller devices, and they get faster and faster and better all the time. But we still have to be very, very mindful about the limited resources on these kinds of things. So being able to take your code that runs on the desktop, on Unikernels, and on mobile, and actually run that on embedded devices is quite nice. Not quite real time, but if you can get away with something like Raspberry Pi, it's very nice. So as far as hitting code reuse, I feel like OCaml does a fairly good job. It covers most of the compile targets I care about. I haven't worked a lot with maybe Arduino-sized devices or real-time devices. And so I would definitely say I have no idea, and I would doubt kind of its ability to go down there. But for the vast majority of the areas that I've worked on, it matches very nicely. As far as correctness goes, just kind of due to the nature of the construction of programs, you get no more null pointer exceptions, no more undefined is not a function. And I spent a sad amount of my life chasing down these. And so I'm always very happy, right, that I don't have to see these. And in Clojure, I still see them. I like Clojure a lot, but I still see null pointer exceptions. Yeah, so this is just an example. So this part that's black right here is actually highlighted very nicely on my screen with a nice error. Just imagine that there was an error there that whenever you...
It's supposed to be red.
Yeah. So just effectively, like you have these very nice tools in OCaml. Whenever you save, it'll immediately tell you, all the type errors, whatnot, as you're used to. But the way tooling is built in OCaml is it's all libraries, and so it doesn't depend on a specific editor. So it's very easy for Emacs or Atom or VS Code or whatever to kind of pull in these libraries and have a very nice editing experience for OCaml. And it's very, very cool if you're working on the backend, you're working somewhere way, way down here, to change some type definition, change some implementation of the code, and actually know that you've broken the client way over here. Oftentimes that is a pretty strenuous reasoning ability or reasoning exercise. So it's very nice to just on save automatically have this happen. So recently I had to do some JavaScript work and some Clojure work. And Clojure is really lovely because you have this live REPL. You can touch your code like in the editor, and you can kind of see what the value is immediately. It just kind of feels like it's alive and you're editing in live. And OCaml is not live, but whenever you save, it immediately tells you, hey, here are all these errors. And it's kind of like both sides are helping you, and you kind of feel this iteration. And then working in JavaScript was amazing because I would save and I would wait, and it wouldn't tell me anything was wrong. I'd save again. I'd save again. And you get so used to this. But then on the other hand, you're like, well, it's running right now. What's the value? And you can't get it, right? You have to go into the browser and get it. So JavaScript has managed to kind of combine some of the nature of Clojure and some of the nature of OCaml in respect to that. But OCaml is lovely as far as that goes. So the performance, generally speaking, is very good. So this is used in high-frequency trading by Jane Street. They're one of the big contributors to OCaml. And so like millions and millions of dollars flow through their system, and they care about performance to a pretty insane degree. It's used at Facebook, Docker, Jane Street, all these other places. Lots of industry use. It's actually quite a pragmatic language. So what's holding it back? There's generally a sense of, if it's 20 years old, OCaml is 20 years old. It's quite aged. If it's that old and it's not very popular, like it can't be that good, right? And so there are definitely problems with the ecosystem. There are a lot of libraries that are not as developed out as on other platforms. There are challenges with the mindset. So because of the very, very kind of systems-oriented nature of OCaml traditionally, it's not really given a lot of tools for web development as of yet.
Do you think Reason is going to fix some of those issues?
All right. That there is hope. So there's lots of problems with tooling and all this other stuff, but Facebook has been investing a massive amount of resources into OCaml, and the big kind of manifestation of that is Reason. And Reason is a meta language on top of OCaml. Any of you guys familiar with Reason? Ooh, cool. All right. I'll try to hurry. All right, so it's a language on top of OCaml, but it's entirely compatible. It is not a fork of the language. Everything works exactly as it did before. It's basically two big things. It reworks syntax, and it encourages kind of a blessed stack approach. There's lots of different tools in OCaml, and they basically say, we're going to make these small subset of tools all work together really, really nicely, so you don't have to spend days or weeks trying to build up something that works for you. And they focus heavily, crazy, on developer experience. So to give you an example, sometimes the type errors can be inscrutable. So this is a expression where we use a string, but it should have been a Boolean in OCaml. And here's the Reason version, where they actually, it's kind of inspired by Elm, where they say, here's the exact line. The types don't match. We expected a string. We wanted a Boolean. They even go so far as like to embed kind of warning and code style in here. So in this case, this is really hard for beginners like to understand why optional arguments can't be erased. And so they actually do quite a good job of saying, here's the optional argument specifically that can't be erased, and here's why. And kind of helping you, it's like having a robotic pair buddy with you, right, as you go along. So there's lots of exciting stuff there. They reworked the syntax to effectively be JavaScript. Yeah, I mean, it's slightly nicer than JavaScript, but what are you gonna do? But it's really, really cool. So this idea of separating syntax from semantics. All right. So the idea is we all serialize to the same output format, right? But syntax now becomes, to a large degree, a render time concern, right? So I like Lisp, and I want to view this AST as a Lisp. You can view it as JavaScript, and other people can view it as OCaml. This means that there are lots of experimentations. Like syntax now becomes libraries rather than a language-blessed concept. So as an example, here's JSX for building UIs. This is actually valid Reason. Someone built a thing. This all desugars statically into function calls that are statically typed. But this helps bridge the gap between a designer who's used to HTML, who wants this kind of thing and wants to be able to express. I know a lot of you are probably revolting a little bit at this. But this has huge implications for actually expressing domain-specific kind of syntax for designers, for systems programmers, for that kind of thing. Yeah, and I think I'm probably out of time. This should be like lots of questions here. Anyway, you also get JSON code. I like Clojure in my list. Buckle script we went over a little bit. Random stuff. So there's new memory profile. We have whole program dead code elimination. Multi-core and algebraic effects kind of coming out. So in case any of these are interesting, feel free to ask some questions.
The audience has got 7 minutes left. Come on, guys.
So for Unikernel deployment, I guess you're familiar with Heroku?
Yes.
So what's great is you can just upload a VM and it starts it when it's needed. What's not great, it takes a long time to start. So Unikernels seem like a great way to solve that.
Oh, yeah.
So is there something like Heroku for Unikernels? And if not, what are the challenges that's holding that back right now?
There is not really. So a company just launched called Deferred Panic, which is working on this kind of thing. But I actually have a small side project I haven't open sourced yet where it's basically a little Heroku built in OCaml. Whenever you compile one of these Unikernels, you can literally drag it into a browser, drop it, and it will be running in milliseconds for everyone else. It's actually incredibly trivial to build something like this because of the kind of the library nature. You can just like slice these things apart and build them very, very easily. Yeah. It's a very fun thing, by the way.
Can you tell us a bit about the algebraic effects?
I can't tell you very much, right? I'm not smart enough, but it has, so there are some really cool things that you can do with it, right? Where typically, so in Haskell, right, all of your effects are statically analyzed and you need to, like they infect the entire call stack. The algebraic effects in OCaml for, I think, largely backwards compatibility are dynamically scoped. What this means is you put a bit of wrapper in here and it's kind of like a try-catch, but instead of catching exceptions, you're catching effects. So you would say, for example, if someone tries to write to the network specifically, I want to actually provide this implementation of the network. And so you can do a lot of cool things where you can say if someone's trying to log, I actually want them to use my log. And so I can capture a lot of that.
Based on continuations?
I believe, actually, I'm not sure entirely. Yeah, so there's a lot of, so multi-core is actually implemented in terms of algebraic effect handlers. And so there's a lot of work to make it efficient. So I'm not sure what the implication of continuations would be there. But Casey does some very cool stuff, and I will link to it in the slides if you'd like.
Is there a package manager, or if there is, how can you distribute code that has some native code for one of the platforms?
There is. OPAM is one of the most colorful package managers. It's very nice. And they have a very different model from NPM, so the packages are actually reviewed before they're allowed into the repository, but it's a very lightweight review process, and there's lots of instructions about how you actually do this kind of thing. Oftentimes, for example, you can do an OPAM depext, which says there are external dependencies that are not in OCaml, and I need like libraries in them, and so you run OPAM depext, and depending on your system, it will actually go and install all those things for you. So it's quite a nice approach.
I've heard a lot about Unikernels. You've also have databases and UI in there. Can you say something about that?
Sure. So the idea, so databases is kind of the Ermin approach. Rather than having file systems and databases separately, what if we could cover some of the use case or a large portion of the use case with an in-memory data store based off of Git that could speak Git. So for example, your Unikernel boots up, and the first thing it does is actually do a Git pull of the state that it cares about from some central Git repository. It can make some changes and can push, and if there's a conflict, programmatically resolve it depending on whatever your merge conflict resolution algorithm is. With the native kind of React native and React integrations, you can build UIs very, very nicely. So we saw the JSX code there, right? This is very familiar to anyone who writes React UIs, and so actually being able to write this code in OCaml and then have it render either server-side or client-side or on mobile, depending, is very nice. And then you're reusing so much of the code across, whether it's validation, parsing, whatever it is. You have this great code coverage across both client and server and kind of the intermediate layer as well.
It sounds a lot like using Flow, right? So how hard is it to migrate JavaScript code base that uses Flow to plain OCaml, like we Reflect?
So actually, I think there's some opportunity. I would say right now it would be quite difficult, right? Especially if you weren't familiar with OCaml and whatnot, it would take lots of work because there's a big ecosystem in JavaScript that you don't necessarily have on OCaml. So porting it over would be challenging. The mechanical translation part is actually quite trivial, though, right? So if you're not worried about the ecosystem and whatnot, it's very easy. All the types are inferred, and it's kind of, it's a considerably easier process, I would say, even than working with Flow generally. But you get a much more sound kind of types of programming. Cool. Oh, sorry.
So you mentioned that you like and work with both Clojure and OCaml, and from your experience so far, where would you use one and when another?
So actually, I lean more and more towards OCaml these days, simply because of the I run into a lot of action at a distance in some of the Clojure code bases, where I'll change something here, and I didn't have the foresight to write all the correct tests to know that I've actually broken something over here. And this ends up kind of leading to this crippling state where you're afraid to make these changes. And we write kind of I work on a financial system, and so correctness is quite imperative in a lot of these cases. Closure is a lot of fun, though. Just generally speaking, it's a lot of fun to work in. Like if you have stuff like Figwheel for live programming, you just I do really like it. OCaml, the REPL story is not nearly as developed. It requires kind of more upfront approach or kind of thoughtful approach. And so overall, like, I don't know, Closure is fun for things I would throw away, right? So like I want to experiment, I want to explore very quickly. But I don't know that I want to rely on it in a month or 2 months or a year from now. Which is not to say that other people shouldn't, right? Just kind of my personal experience after 4 or 5 years. Yeah, sorry, I didn't mean to be inflammatory there. Closure is great. Use Closure. It is cool. Yeah. Cool. All right, thank you very much.